My name is Steve Rhodes, and you're listening to a recording of a presentation given at the ESWP International Bridge Conference in Pittsburgh in June 2014. I hope in this presentation, as in the paper on which it's based, to bring your attention to some of the latest practices, many of them from recent UK recommendations regarding integral bridges and the modelling of soil structure interaction. Now, jointless bridges aren't new. In fact, the Romans built them, and we can immediately say that jointless bridges can be very durable. Pont de Garde here is very nearly 2,000 years old. When Jean-Jacques Rousseau visited in 1738, he wrote, "I said to myself with a sigh, why was I not born Roman?" Many of us probably feel like that when we look at this. Instead, often we go out on bridge inspections and perhaps you have a sorry collection of photos like these damaged joints, and underneath bearings and girders, suffering because of water leaking through, and depending on the climate, probably with de-icing salts as well. So around the world now we tend to build jointless bridges. There are many aspects of jointless bridges we could be discussing, and I'm sure many of us have views on particular details and so on, but I'm speaking today about how we take account of or calculate the earth pressures on integral abutments. Now, integral and semi-integral bridges accommodate thermal expansion and contraction by movement of the abutments, the end screens. And those are essentially retaining structures. And retaining walls are often analysed representing the soil as a load only. We assume active pressure in some regions and passive pressure in other regions. The stiffness of the soil doesn't come into it. Now, of course, in real life, it's more complex. As the structure moves away from the soil, the earth pressures reduce from the at-rest pressure towards the limiting active pressure, Ka. On the other hand, when the structure moves into the soil, earth pressures increase towards the passive limit, Kp. But the actual earth pressure may be some intermediate value, depending on the strain in the soil, depending essentially how much the wall has moved. In fact, in bridges with deck joints and bearings, the abutments are typically subjected to only pressures between at-rest and active, so they're low pressures. In integral abutments, when summer comes, the deck expands and the earth pressures will be significantly greater. But there's more. From winter to summer, the earth pressures increase with an accompanying change in the bending moments, which is illustrated here. But the repeated cyclical movement of the integral abutments causes particle realignment in granular backfill. So each year, while the winter pressures don't change much, the summer pressures, the peak summer pressures, get greater. So we see here the moments in the abutment walls increase each year as the backfill becomes stiffer each year. It's called soil ratcheting. And this process only tails off after 100 to 200 cycles. The pressures behind integral abutments built in the last 20 or 30 years are therefore still ramping up now. Now, clearly for design, we ought to have a good idea what the lateral earth pressures are going to end up at, given a design life of the order 75 years, if you're working to the LRFD specification. But there's no standard approach for determining earth pressures for integral abutments in the LRFD code, nor are there any in the Eurocodes. However, there has been quite a bit of research, and this has recently been brought together to define some recommendations published by the British Standards in PD 6694 Part 1. This pressure distribution from that document reflects how the densification of the backfill gives quite a significant increase in earth pressure over the top half of the wall, where the movements are greatest, and has a relatively lesser effect lower down the wall. Now, that distribution is for full height abutment walls, where the thermal movements are accommodated by rotation or flexure. so full height. For short walls, as in bank pads or end screen abutments, thermal movements are accommodated by pure translation. For those, we can use a much simpler triangular pressure distribution. But for both cases, we have this special earth pressure coefficient for integral bridges, generally given the symbol K star. And the question is, what value should we use for K star? That's where this document, PD 66941, gives expressions which have been validated against a wide range of research on integral bridges. For full height abutments, K star is based upon the at-rest pressure coefficient, K0, the passive pressure coefficient, KPT, the wall movement range at mid-height, D', which can be taken as between 0.5 and 0.7 times the movement at deck level, so probably 0.5 for the piled wall, and a coefficient, C, which is based on the elastic modulus of the subgrade. It's expressed here, as in the paper, for an elastic modulus in KSI. The PD, being British, gives this in terms of MPa, of course. For bank pad abutments, where the movement is translational, it's a similar, actually slightly simpler expression. So we can calculate the earth pressures using K star and apply them to an analysis model of the bridge. It's called a limiting equilibrium approach. We need to consider the minimum earth pressures, active, Ka, as well as the maximum, K star. And PD 6694 Part 1 also gives guidance on appropriate pressures for wing walls, bearing in mind this soil ratcheting effect. I've illustrated a short span slab deck bridge, modelled with shell elements here, but it's worth considering for a moment the structural idealisation of the bridge itself, because shell elements are designed to handle shear, bending, twisting and in-plane forces in a way which correctly represents slab-type members. So they can be used in models of slab and girder decks by mixing the elements with beam elements in a so-called plate eccentric beam model, or we can use a full 3D model. Here we're using shell elements to represent the slab, and here the girder webs too, while the top and bottom flanges can be represented using beam elements, and stiffeners and cross bracing can also be represented using 3D beam elements. I mention this because it's tempting to persist with our grid or grillage modelling approach, because we're familiar with it. We've got wizards which help us. It's tempting just to extend the idea into 3 dimensions, with the abutment walls treated as grids too. Well, we know there are some drawbacks of grillages. The NCHRP Report 725 says that the conventional 2D grid models used in current practice substantially underestimate the girder torsional stiffness in I-girder bridges, substantially misrepresent the cross-frame responses, and do not address the calculation of girder flange lateral bending in skewed I-girder bridges. But for integral bridges, there's a bigger problem with trying to move from those 2D grids or grillages to a 3D version of them. And once we try to apply in-plane loads to a grid model, it's constructed now of 3D beams, we find difficulties arise when in-plane effects are considered. The real problem is the occurrence of local in-plane distortions of the grillage members, which are clearly inconsistent with the behaviour of the bridge deck. In an integral bridge, there are obviously in-plane forces on the deck, and real concrete slabs don't deform with this in-plane bending. There's no such thing. So we need to think in terms of shell elements to represent slabs. But whatever way we model the structure, be it some sort of 2D plane frame perhaps, or a 3D model like this one, in a limiting equilibrium approach, the soil is represented only as a load. This is not a soil structure interaction analysis when you're using K-star. This is a way of avoiding a soil structure interaction analysis. So when we have structures where the soil stiffness plays a more significant role in the behaviour of the system, the K-star approach is not adequate. For example, these common integral bridge types, including embedded walls, and those including bank pads on a single row of piles. To model this soil structure interaction, SSI, we can typically either represent the soil as a continuum or using springs. In this underpass with embedded walls, a 2D continuum model has been used. Here the structure is represented using 2D beam elements, while the soil mass is represented using plane strain elements. Now, continuum elements are perhaps less familiar to bridge engineers who prefer to deal with beams and perhaps shells. As we're now modelling the soil mass around the structure, some new questions come. For example, how far out do we need to model? Where the boundaries are not defined by something physical like bedrock or a cliff face, we have to test our model to ensure that our assumptions about the location of the model edges don't introduce a significant inaccuracy. In fact, we can test if the width of the model is sufficient by changing the support conditions at the vertical boundaries. If we add a vertical fixity and the soil gets sort of snagged up at the sides, and this actually changes the results in the area of interest at the structure, then the soil block isn't wide enough. So we need to make it wider and add more elements. It's important to have the flexibility to just be able to stretch the model out without redrawing all the elements. And for the bottom boundary, the horizontal boundary here, we just have to make the model deeper again until the changing key results in our structure is negligible compared to other assumptions inherent in the analysis. So our checks need to include the width and depth of the soil block. We also need to be mindful of element shapes and aspect ratios and mesh refinement, just as we are in all finite element analyses. All of these require software which will automatically remesh your model based upon straightforward changes to the geometry, giving you good shaped elements and allowing you to change the number of elements easily. Otherwise, this will become very time consuming. Next, we need to think about the material that we use to represent the soil. If we start with a homogeneous isotropic linear elastic material, that requires only elastic modulus and Poisson's ratio to define it. But soil is generally better represented with some nonlinear material. Probably the most widely used is the more Coulomb material. And this illustration shows the yield surface, and it's about now that many people start to tune out and think that this is probably quite academic, and we're going to start talking about yield, which is based on a critical shear stress and pressure dependency and all those things. But thinking practically, what this illustration is telling us is that the strength of the material increases with balanced confining stresses. So the strength of the soil is greater as we go deeper into the ground, which of course we know. So to bring the way this material works in your model back to basics, we can do a test model, a block of soil 30 foot by 30 foot. So we can calculate the pressures by hand. The vertical stress at the bottom of the 30 foot block would be 3.379 kips per square foot. The at-rest pressure at that same level would be 1.7, and the passive pressure would be 10.137 kip per square foot. So here's the block. We move the right boundary as if it's an abutment wall being pushed into the block by some thermal expansion. Stresses in the soil increase. Finally, they reach the expected passive pressure and they don't exceed it. We could do the same in reverse and find the decrease in stress to the limiting active state. These states are reached at a strain, a measurable deflection in this model. So test models matching numbers like this, it gives us some confidence, some understanding of how the material will work in a more complex model. It's worth noting, though, that the initial stresses, K0, assumed in the model will have an effect upon the movements required to mobilise the active and passive limits. It won't change the values of the active and passive limits, but it changes how much movement is required before those limits are reached. And that's something unpacked a little bit more in the paper. So we've got our model with more Coulomb material or other nonlinear material model. But wait, we've forgotten something. More Coulomb material was designed for regular soil. It wasn't designed to take soil ratcheting into account. So there's some good news and there is some okay news. The good news is that for a piled or embedded integral abutment with cohesive soils, retaining cohesive soils, strain ratcheting may be ignored. And since often embedded walls are built by top-down construction, often the retained material is the naturally arising material rather than granular backfill. So in those cases, we can use a conventional soil structure interaction analysis. The okay news is that for granular soils, PD 6694 Part 1 gives a method in Annex A describing a way of modifying the elastic modulus of the soil continuum over the top part of the wall where the movement is most significant, and so where the ratcheting effect is most significant. That modification is based on the K-star equations that we looked at earlier in this presentation. The only difficulty is that we need to determine the effective height in those equations with a little bit of iteration. So we've got our model with more Coulomb or other nonlinear material, and we modify the Young's modulus for granular soil based on K-star formulae. The other considerations in our model would include how to represent the interface between the soil and the structure. Now for this, you need software which will allow you to select either joint elements, contact slide lines, or elastoplastic interface materials. Any of these can be suitable. The crucial consideration in modelling here is usually the back of wall friction angle, delta. Delta can't be more than the internal angle of friction for the retained soil, and it can't be less than 0, because 0 means a notionally smooth wall. In many retaining structures, it is conservative to use delta equals 0, but in integral bridges, upper bound values may also be critical. The UK recommendations suggest using half the internal angle of friction. So there's our continuum model with a reminder of the considerations, including the frictional interface. And this approach is very suitable for embedded walls. But we still have the abutments or bank pads on piles where lateral movement at the pile head does not infer plane lateral movement of the soil in the same way that movement of a retaining wall does infer plane lateral movement of the soil. There may be some arching of soil between piles. There may not be so much. Some judgment is needed. This makes continuum models less attractive and the use of springs to represent the soil more attractive. So we can model our integral bridge with bank pad on piles, perhaps using a 3D model where the deck is represented with shell elements or a mixture of beam and shell elements, probably not a grid, not a grillage. The end screens or bank pads are similarly either shell elements or 3D beams or a mixture. It's quite reasonable for the lateral earth pressures on these end screens to be at minimum Ka and at maximum K star, using the approach I described earlier. Below, the piles are modelled with 3D beam elements, with the soil represented using springs or nonlinear joints. Indeed, this is the approach which Majeski and Masters took on this integral abutment bridge in Louisiana, linear springs for the soil, 3D beams for the piles, deck and end screen modelled with a mixture of shell and 3D beam elements. The springs we see vary with depth down the pile length. That looks like a simple linear increase with depth, but there's useful guidance on the variation of horizontal modulus of subgrade reaction with depth, such as from this book by Rumbach from the University of Hamburg-Harburg. We also need to take account of the slope. Because of the front slope, the stiffness and strength of the soil, as represented by any spring or nonlinear joint, ought not to be as substantial as that attributed to the soil behind the abutment. Added to that, the remoulding of soil over many thermal cycles should be taken into account. This API publication brings together methods for defining load deflection curves for laterally loaded piles appropriate to various soil materials under static or cyclical loading, and I'd recommend it. Comprehensive software should be able to handle the nonlinear PY curves, which also change with depth. For a full height abutment on piles, however, we need to model both springs along the piles and the earth pressure on the wall above. Mixing a continuum approach and a spring approach is probably going to get messy, so it can be useful to use springs for the wall as well. We can use springs or nonlinear joints which effectively yield at the active and passive limits. They have a stiffness, KH, which is the horizontal modulus of subgrade reaction. Critically, joints like these need to be preloaded with initial stress. They need to start out with an at-rest pressure, and then they can behave appropriately based on the movement of the wall, reflecting the strain in the soil. Now, with the at-rest pressures varying with depth and the limiting pressures varying with depth and the spring stiffness is varying with depth, as we discussed with reference to springs with piles, there's a lot to keep track of. And since there may be a need to modify these values to take account of ratcheting, the software should give you control over all those parameters. Flexibility, but some means of defining the various parameters in a way that is comprehensible, controllable. So let's just summarize, reflecting on those various integral abutment types and the analysis approaches which are most appropriate for each. A full height integral abutment on pad footing. Full height integral abutment on piles or a bank pad. Well, they can typically be analysed with a structural model and soil pressures based on a K-star approach. Now, since for these construction types, granular backfill is usually installed behind the abutments, strain ratcheting must be taken into account, and the formulae for K-star in PD 6694 Part 1 actually incorporates that. For an embedded wall integral abutment, a soil structure interaction analysis is required, typically a continuum analysis. To account for ratcheting, the elastic modulus can be modified using formulae based on the usual K-star formulae. But there's no need to take account of ratcheting when the retained material is cohesive. For abutment walls on a single row of piles, we can represent the soil around the piles and behind the wall using springs or nonlinear joints. Again, with granular backfill, we would typically need to adjust the spring properties by the wall to account for ratcheting. For the popular bank pad on piles, the soil around the piles is modelled with springs, while the backfill pressures can be included as a load using K-star values, and the K-star values should again reflect the ratcheting effect in granular backfill. That concludes our presentation. We hope you found it informative.